Okay, good. So, all right. So what I wanted to start showing you was stuff to do with the GPIO, and uh, so basically GPIO. You remember where you guys plugged a fan into your thing? There's that row or two rows of pins. Okay, so those are GPIO pins, and what they enable you to do is you can plug, well, all kinds of things into them. Now, we plug the fans in to, well, either 5 volt or 3.3 volt. That was up to you. And then the ground pin, and there's a bunch of different ground pins. Um, and and okay, in that case, obviously, it just turned on the fan, right? Because the pin was always on, and the ground is always ground. But it some of the other pins on there you can configure to write or read from in software, okay? And furthermore, some of them have fancy capabilities to basically be like transmit and receive pins. So you could connect sort of peripheral devices like sensors or like a GPS unit, for example. You can connect to it, and then it would transmit, obviously, both to have the thing be on and off, but the data of what the GPS unit was receiving, you could communicate with that chip and get information back and forth, and yay. Okay. Um, so the way that this works on the Pi um, is it uses, well, or at least how you access it in Linux on the Pi, uses a technique called memory mapping. Okay. And to demonstrate memory mapping, actually, probably the easiest thing to do is let's go way back. Okay. So let's actually look just briefly at the 8-bit Nintendo. Okay. So I'm going to load, this was 8-bit Workshop, our little fun little thing, and it'll take a minute because I need to run an Ethernet cable. Okay. So the way that on the if I go to memory, it's either browser or map. I think I want map. All right. So the way that on the 8-bit Nintendo, you interfaced with the audio chip, the video chip, the controllers, all of that sorts of stuff, is that they were memory mapped. Okay. So for example, um, the PPU or pixel processing unit um, started at memory address 2000. Okay. And so if you wanted to write data to one of the PPU registers to do something, you would write data to a memory address, but it actually went to the PPU or the pixel chip. Okay. So you're sort of using the memory address space, some of it not actually for memory. Okay. And then your address bus and your circuitry would have to be able to say, like, oh, this thing starts with a 2, not a 3. That means I should route the signals over here to the PPU as opposed to RAM. Okay. So on the machine, even though RAM address 2000 is a, like, theoretically a place that RAM could be located, it didn't actually get used for it. Okay, so there was no RAM that had that address on the 8-bit Nintendo. Okay, um, and then other stuff is allocated differently. So, for example, there's the registers here starting at 4000. Um, was the APU, or audio processing unit. And so if you pushed data to there, it would make sounds and stuff. Okay. But all of this stuff you access by writing data to memory, and then the way that the circuit board and stuff is laid out is that it accesses that. It goes to the appropriate chip, and the chip does whatever it's supposed to do with that data: sound, video, whatever. Okay. Okay. So it's like that for us on the Pi with the memory map. Okay. Except the addresses obviously are 64-bit addresses, and we just have to know what devices and what is assigned to which little piece of memory. Okay, we'll talk maybe some of those more details a little bit later, um, because for technical reasons, I don't have it working yet. Um, so basically, all of the devices that are on the Raspberry Pi are mapped to sort of a little segment of memory. And if we want to say, for example, turn a pin on or off, or configure it to be an output versus an input or whatever, um, then what we have to do is write data to the appropriate bits of certain locations in memory. Okay. And that writing data to memory is not anything new, right? We've done that before. It's just that you have to write it to a particular address rather than, something relative to your stack or whatever. Okay. And here lies the problem. So I wrote a simple program to configure one of the pins to be an output and turn it on. Everything looked good. Assembled it. Great. Compiled it or linked it. Great. Ran it. What did I get? Seg fault. Okay. And the reason I got a seg fault is because the memory address that I was trying to write to was outside the memory segment that the operating system had allocated me. So I was trying to write to a place I wasn't allowed to by the operating system. Okay. If I wasn't running an operating system where I could just do whatever I wanted, then I wouldn't have had that issue. But alas, we have operating systems. Okay. So the fix is there's basically a giant initialization routine that takes up 3 pages worth of code in the textbook. And you know what I discovered yesterday? All of the code that's in the book, where is it? There's no like online, hey, here, download this zip file that's got all of the code from the examples that he's got in the textbook. The, I couldn't find it. I found it for one of his other older books. Um, no, I didn't do that because it was 10 o'clock last night when I hit this problem, and I was like, I am not sitting here and typing 3 pages of assembly out by hand. Like, I just don't, I can't do that right now. So anyway, so I wrote to the guy to see if he has that, um, because that would be really handy. So I did find the 32-bit variant from his previous book, but of course all the assembly is 32-bit assembly, and I would have to go through and change everything, and that would have been just as much as typing it all out from scratch. So I said, F that. Okay, for now. But what I wanted to do, just to kind of give us a wet our palate for where we're going to go with this, is I did build a simple circuit, and we can actually access the GPIO pins not through assembly yet, but we can do it actually through Scratch. So I never thought I'd be doing this today, but hey, whatever, it works. So the other thing that I started playing with is I was like, oh, okay, well, if I'll just use a C library to access the pins and get control of them, and then we'll do the rest of it in assembly. Well, what's one of the minor problems with a bunch of the libraries they're all 32-bit, not 64-bit. So I'm like, well, crap, that won't work either. But anyway, all right, so I'm going to try something here I'm going to try using the document camera as an input for OBS, and we'll see if this works. I did it once before, I think, but there I was using the Elgato, and I only have one of those things. So let's try and see if this works to use it as an OBS input. All right, so let's do, so doc cam. It's going to go blank for a moment. Okay, this would probably be a video capture device. Nope, it is not that. Yeah, that's probably, okay, so this would be, let's see, let's see, well, we've got display capture, image, slideshow, media source. I mean, video capture device is what a webcam would be. Oh no, there it is. It just wasn't on yet. Okay. Not getting video. Yeah, it's detecting it. I just need to. All right. Use preset. Let's try just high. No. Well, no, I can't see anything on the screen, even though it's. Maybe I have to change something on here. Um, well, all right. This was a brilliant idea, but alas. All right. Well, that's not going to work. It was a good idea, but that's all right. So let me go back to the Elgato. Basically, what I wanted you to do is be able to see what I'm doing on the Pi here. So, um, so what I've got is a breadboard, this little ribbon cable, and then a little header pin that breaks out all of the pins that are connected to the ribbon to either side of a breadboard. And then I just connected a little light on here, nothing fancy. Okay, so if I go into Scratch, actually, can at least demonstrate the the idea here. So I'm gonna have to. The annoying thing here is you have to pull the fan because you have to plug this whole bloody thing in. Um, Come on, and of course get this all to line up. There we go. Okay, so I've got it plugged in, and you guys will just have to trust me that it's actually going to be working. So I'll just kind of lay this up here, sort of. There, I can dangle. Okay, so what I can do is first thing I need to do is throw in an extension because I want to use Raspberry Pi Gpio, and that gives me a couple of other things here. And so one thing I could do, for example, so I can just say, okay, when I start the program, repeat forever, um, set GPIO pin, I connected it to pin 17. Oops. Wait a second, set it to low, and wait a second. Okay, so if I run that, then what happens? Ah, voila. Okay, so I'm turning the light on and off. Okay, wonderful. So how is this actually working? Well, Scratch, of course, being a visual language, it's hiding a lot of the details from us because it's designed for children. But what is happening is that in order to set a pin to output mode, I need to write 3 bits of data to a certain spot. Okay, and those 3 bits of data tell the device manager, the chip thing on the Pi, how that pin is going to be configured. Is it input? Is it output? Is it, there are all kinds of these alternative functions. Okay, so I need to set it to output, which happens to be 001 is the setting for output. Okay, then to turn the pin on and actually apply power to it, I need to write a bit of a 1 to another spot that basically says, so bit number 16 of a particular range or particular address controls pin 17, right? Because there is no pin 0. And I write a 1 to that and it turns it on. Okay, then how do I turn it off? What would be logical? You put a 0 in that same bit? Oh, that would be too easy. No, you write another to a different range of memory, you write a 1 to bit 17, and that you write a 1 to that, and that turns it off, right? So there's a set and a clear bit that you set. I don't know why they did it that way, but whatever, that's what they did. So great. It just stays there, and then when you write to it again, it like the chip detects that segment of memory has been written to, right? And then it does something. Yeah, I was a little surprised that they chose to do it that way too, but whatever. Um, okay, so um, yeah, that's what they did. Okay, so what's happening here with Scratch is that on the back end, there's some stuff that we can't see that's basically doing all of that for us, right? And then what we'll obviously have to do is talk about how to do this in assembly um, and where to put what bits and so on. Okay, not a particularly fancy fancy program, and uh, let me duplicate this bit, and that just should turn the pin off. Okay, so I'm not leaving it on the whole time. Okay, so that's basically the idea. Now, the reason I wanted to talk about this is sort of a bridge to the next sort of final big chunk worth of the course, and that's actually to start talking about sort of circuit level architectural business. Okay, and for that, let's quit this and quit this, and we're going to use another program called Logisim. Now, it's a Java program, and you can run it on your regular computers too. I went ahead and put a copy of it on here just for convenience. Um, The one annoying thing is to run it, you have to run it through the console, even though it's a graphical thing. I haven't gotten the like a magic button to work. And the way you do it is easy. It's just java.jar or dash jar and then the file name. And it'll take a minute to fire up. Okay. Now, one thing to note, if you terminate that console window, what happens to the program? Poof, it just disappears. Okay. Don't do that because you won't get a prompt. Are you sure you want to quit? Would you like to save your data? Nope, you won't get anything. Just gone. Okay, so don't do that because that's bad. Okay. All right, so let me minimize this so that I have less of a chance of screwing this up. All right, so here's what we've got. Right now, it's a blank canvas. Wow. But what can we put in this thing? We can start to build sort of schematic level representation of circuits. Okay, so for example, let me take an AND gate. All right, and then let's see, let me go into wires, and then I'll do, say, input output. Okay, so for example, I could have two inputs and an output, and then I can wire these dudes up like so. Okay, and I think I can zoom this. Yeah, here we go. All right, so I'll zoom it in, right? All right, so what do we got here? What's the big old thing in the middle? Is an AND gate, right? So what does it do? It does logical AND of the two bits that are coming into it, right? And what is 0 and 0? Well, 0, right? And so that's why the output's a 0. Then if I change my tool from the pointer to the little finger, then I can poke and change either of the input bits to a 1, and the circuit will react accordingly. Okay. What's nice about this is I don't have to like worry about the resistors or any of that kind of stuff. It's just sort of schematic and magic that it's happening. Okay, so you can't really do this and then like magically build a circuit that looks just like it because you'd have to put in the resistors and capacitors and all of that jazz, and I'm not bothering with that for right now. But we can do something like that. Okay, now, so there's a whole bunch of pieces in here, including transistors. Um, Pole resistors, you have to use those with inputs, so we'll talk more about that once I get all the GPIO crap working. And then there are little splitter things. So, for example, if I want to build a full-fledged computer in this thing, well, what do I need? I need memory, I need a processor, I need an instruction decoder, I need registers, right? I need all of these sorts of things. Okay, and the question is, how do we build all of those sorts of things? Well, the memory, let me delete all this. The memory is easy. Namely, you go to memory, and what kind of memory do we want? Let's say RAM, and we plop this big old thing. Okay, and then if I click on it, then I can configure how much memory is it. Okay, well, what do I need to do to specify how this memory is going to work? I need to say how much that came back. Let me double check. Okay, so what is the address width and what is the data width? Okay, now for us, on the Raspberry Pi, what is the address width? Huh? address width, that's the instruction width. Yeah, the addresses are all 64 bits, okay? What are the data widths? Well, there we could argue a little bit. Maybe it's 32, maybe it's 64, because it is possible to write 64 bits at a time, right? But each byte, each memory address holds only 8 bits, okay? So the default when you plop one of these things down is an 8-bit address width and an 8-bit data width, okay? And then you see at least part of the memory looking here, right? And if I, oops, wrong keyboard. If I double click on that and I go to, let's see, where is it? Show contents or edit contents, then you can see everything. You can hex edit it, and you can even load and save data to a file so that you could load something in that you'd either pre-written or saved before. Okay, so right now it's 8 data bits and 8 address bits. And there is the entire segment of memory. Does that look familiar? Yeah, how does this look familiar? Yeah, this is exactly the Brookshire memory architecture, right? Okay, because on Brookshire, right, you have 256 bytes of memory. Each one takes exactly 1 byte to address, a low byte and a high byte, or nibble, sorry, low nibble, high nibble. And each address can hold a single byte, right? Well, there we go. This is Brookshire memory. All right, if I wanted to scale this up to, oops, so let me close this and let me change, I'll leave the data bus the way it is, but I'll change the address bus to, um, 16, okay? And I'm not sure why graphically it uh, didn't update this. Um, oh, okay, separate data, one bidirectional data bus, we'll do that. Here, let me scooch this over. Oh, dang it. Okay, so here is where the address goes, right? So you plug it into here, and then this little dude there is a splitter that basically splits out, so you can have a single wire carrying 16 bits worth of data, but really what is it? It's 16 wires, right? They're just kind of bundled together for making the graphics nice. Okay, fine. And then we've got the data bus, which goes which is the 8-bit thing over on the right. And you can configure this in 2 different ways to have something where it bidirectionally reads and writes in the same pins, or you can have it read on one side and write on the other. Okay. Okay. And then there are 3 other pins that we need that are up in the top left. Okay. Write enable, output enable, and then C1. Well, C1 is where we would connect a clock. And we'll talk about the clock stuff later. But basically, uh, stuff happens on the rising edge of clock cycles. Okay, so when a clock cycle is going to go 0 to 1 and back and forth. Okay, magic happens when you make the transition from 0 to 1. That's when stuff would occur. Okay, and um, now on a Okay, audio's back up. I don't know why it keeps cutting out. Okay, on a real machine, when I say clock for the memory, that's not necessarily the same as the clock for the processor, right? These things can have multiple clocks, and your memory doesn't necessarily operate at exactly the same frequencies that your processor does, right? Sometimes it's more, sometimes it's less. It just depends on, are we talking a GPU, a CPU, or do you have DDR this, DDR that, right? Whatever. Okay. Now, if we were to build like a simple Brookshire level machine, though, these would probably all be exactly the same clock. Okay. Um, okay. So if I have 16 bits worth of address space, this memory module would be like the memory module on the 8-bit Nintendo, right? So the 8-bit Nintendo's processor, Apple II, Commodore 64, all of these guys, it was called the Commodore 64 because it had 64 kilobytes of memory, okay? And that corresponds to a 16-bit address space, okay? So 65535, 64K. Whopping fast and whopping amounts of memory, right? We played games on 64K. Can you believe that? And nowadays, the game logo wouldn't even fit in. Is anybody geared up to buy a RTX 370 here in 21 minutes? Yeah. Yeah. All the eBay bots. Yeah. Hmm? Yeah. So anyway, um, all right. Well, whatever. Okay. So that's the story on memory. Now let's dive in a little bit deeper and see actually how this is working. So let me delete that. And what I'm going to do is I'm going to make a D flip-flop, okay? And we can talk later about the circuit level component of this. All right, let me put an input pin, and let me put an output pin, and let me connect this and this. Okay, so if I toggle the data pin, what happens? Absolutely nothing, okay? Because I haven't connected it to a clock. All right, so let me go up and let me get a clock. Okay, and then under simulate, I'm going to say tick frequency. Let me do a half a hertz. Okay, so we can see it nice and slow. And then I'm going to ticks enabled. Okay, and then my clock will operate at 1/2 hertz. Okay, which is, yes, very slow, but it's slow enough that we can actually watch it. Okay, how fast would this normally operate for a processor? Yeah, mega or giga kind of hertz, right? So your processors from the 80s were operating at like 5 to 10 megahertz. Um, you know, the first computer that I built that was mine, I had a 90 megahertz Pentium processor. Yeah, it was like, right? The height of luxury. Okay, so what's going to happen to the data if I, oh, wrong mouse, if I click this, okay? So when did the write to the data, to the memory actually happen? The next time the clock went from low to high. Okay, so it happened on the rising edge. Now, one thing that's a little bit slightly misleading about a simulator like this is it looks like it happened instantly, right? Is it really instant? No, of course not, right? It's just really, really, really fast relative to the speed of the clock. Okay, now if I put like 10,000 of these things in a line and it takes like a nanosecond for each one, then what's going to happen is that the subsequent ones are going to be off by more and more and more time, right? And if that delay is big relative to the clock speed, then what you can get is called clock skew, and weird crap can happen. Okay, so don't do that. Okay, now watch though what happens when I put the data pin back to 0. Okay, what happened? Yeah, it wrote the 0. Okay, so this circuit or this thing that's in the middle is called a D flip-flop, and D for data. Okay, it has two pins that we haven't used here called S and R, set and reset. Um, we could use those basically like to clear out all of memory and basically write zeros to everything instantaneously, which might be kind of useful for a reset switch or something. Um, but we won't use those, okay, for now. And so let me delete this wire. Oh, I keep using the wrong mouse. Let me delete this wire for right now. Oops, that is not what I meant to do. I meant to delete the wire. Oh, it's because I've got the, there we go, okay. Okay, so I'm going to add one little thing here. I'm going to add a pin, and I'm also going to add an AND gate. And the nice thing about these pins is I can label them. Okay, and let me zoom out a little bit. And then I'm going to put this back here. Okay, so now under what circumstances will data get written to it? Huh? When I want it to, okay? Meaning that it will only happen when the output of that AND gate is a 1, which means that the clock has to be hitting a rising edge, and I need to have the write enable set to a 1. Okay, and otherwise it's just going to sit there and preserve its contents. Okay, so if I click here, watch. Oh, I'm sorry. I'm writing a 0 to it. Okay, so let's say I want to write a 1, write enable. Okay, and then if I turn this off, the write enable, it preserves that bit even if I change the data bit back to a 0. Right? Okay, so so we could bundle this little thing up and make that its own little unit, right, that has 3 inputs, a data bit input, a write enable bit input, and the clock, and one output, namely the data. Okay, great. Does that make sense? Okay, so what you're looking at is a 1-bit cell of memory. So how could I make RAM that has 256 bytes? I need a crap ton of these things, right? Because this is exactly 1 bit. So if I wanted 8 bits or a byte, I would need 8 of these things. And then if I want 256 bytes, well, then I need 256 of those little 8-bit units, right? Okay, and now you can see where this starts to go. This starts to get into inception territory, right? Because we've now said, okay, if I can build one of these, I can build 100,000 of them. So let's just build 100,000 of them. Okay, now, if I copied and pasted this thing 100,000 times, I mean, it would be a nightmare of wires and stuff, right? But from a circuit standpoint, that's exactly what has to happen, like for you to build a chip, right? You have to have software that can keep track of billions of transistors and the other things, right, that you need, and lay it all out in, however many layers that they build these things out of, and hope that when you fabricate this, it won't get screwed up. Um, this is why processors cost money. Well, because you don't get 100% yield when you fabricate one of these things. They will have defects. Okay. In fact, that's actually apropos because in 13 minutes, when the RTX 970s, or sorry, 3070s launch, and in 14 minutes when they've sold out, uh, what's the difference between an RTX 3080 and an RTX 3070? You guys don't keep up with this stuff? Huh? Well, it's, yeah, okay, but okay, so other than $200 or whatever. Okay, yeah, the 3080 has more VRAM than the 30. So the 3080 ships with I think 11 gigabytes, and which is a funky number, but whatever. Huh? Well, I don't know if you want to do 60, 120 frames a second for a 120 hertz monitor at 4K. You need, you quote need.
Just do low settings, turn off your frame count, we're chilling. You can have like 300 with a 144 hertz monitor.
Yeah. Well, anyway. Okay, so what about the processor? That's the part of the GPU, the actual onboard processor. So what's the difference between, say, the 3080 and the 3070? Are they physically the same processor? In this case, no. But in other cases, so like let's take, for example, a um, a quad core. Well, okay, maybe AMD stuff is a little easier to say this. What's the difference between a 6-core Ryzen processor and an 8-core Ryzen processor? Okay, obviously 2 cores, but right, I mean, that sounds stupid, right? Okay, but are there 2 separate assembly lines, and this assembly line A is making 6-core processors, and assembly line B is making 8-core processors? No. There is one assembly line making 8-core processors. So how do they end up with a 6-core thing at the end? Yeah, exactly. So it's called binning, right? So they take the thing off the fab, a supposedly 8-core processor, and they're going to run a diagnostic test, well, lots of them, to make sure that the thing came out okay. Well, what happens if you've got a perfectly good processor, but 2 of the cores are defective? The other 6 pass every test. Then it's a 6-core, you laser fuse off those 2, and now you have a 6-core processor. Right? Now you can't sell it as an 8-core processor because it's not. But you could sell it for a little bit less as a 6-core processor. And what's the alternative? Throwing it in the garbage, right? Well, okay, which is better for your bottom line as a company? Selling what otherwise would be garbage for less money, but still getting some money out of it. Okay. Right. So companies do this with GPUs. Now, in NVIDIA's case, I think the 3080 and the 3070 are 2 separate processors. But then what they'll do later is they'll say, okay, we'll launch the 3060, and it'll be the 3070 where we fused off the bad cores. Same chip, but we were able to recoup some of our defective parts, right? Yeah, it's not in the GPU world. It's not 100% as easy to do this, but that's basically the idea. Okay. All right. So if we wanted to build a computer or start to build a computer, we just need crap tons of these things, right? And so a register or a memory cell is going to be a bunch of these put together, one for each bit. Okay, and then we'll aggregate them. So like, let's make a single byte memory unit. Okay, does that sound good? All right. So let me turn off the ticking for right now. Okay, and what I'm going to do is I'm going to delete this for right now. I'll put it back in a minute. Okay, and because what I'm going to do is I'm going to rename some of these things. So I'm going to rename this guy um, write enable. Okay, and then I'm going to make a pin and I'm going to call it clock. Okay, and then I'm going to delete that and do, let's say, data out, and this one I'll call data in. Okay, so then what I'm going to do is I'm going to select all of this stuff. Okay, and I'm going to let's see, where do they put this? Okay, I'm going to make, oops, I did this backwards. Okay, so I'm going to copy all of this. I'm going to make a new circuit, which I'll call single bit. Okay, I'm going to paste this here, maybe. Okay, let me actually do it this way. Where did it go? Oops. Okay, I've called this thing main, which is not what I meant, but so what I can do is I can take the object called main and plop one of these things down, right? So this thing right here is the circuit that we made a minute ago. I just shouldn't have called it main, but whatever, okay? So if I wanted 8 bits, what do I need? I need 8 of these. Okay, so there's, you guys can see what I'm up to here. Let me zoom out a little bit more so that we can see this easily. Okay, so there's 4 of them. Let's put down our other 8, or other 4, rather. Okay. Okay, so this would be 8 bits, but what we would have to do is, so what would come into this circuit? What needs to come in is a write enable, and that's going to be a single bit, okay? But what else do I need? Let me scroll. Actually, let me scooch these things to the right a little bit. Okay, I'm going to need a write enable, but I'm also going to need data coming in, right? And so let me call this data in. But how many bits of data would be coming in? 8 bits. Okay. And then what do I need to do? Well, I need to use a splitter, and it needs to fan out by 8 because its bit width in is 8. Okay, and then I would plop this thing, oops, here. Okay, I also need my clock. Okay, so what do I have to connect to where? Well, I need to take the write enable and the clock in and connect it to all 8 of those. Okay, what about the data that I've peeled off with this splitter? And it's a little hard to see on the projector, but can you see that each of the little split pins is labeled 0 through 7? Yeah. And also you can reverse the order. So in this case, 0 is at the top. It might be easier to have 0 at the bottom for whatever reason. So you can change it to be that if you need. But what do I need to do for my data pins? The 0th one goes to the guy at the top, and the 7 goes to the one at the very bottom, and then all the other ones in between. Like Monday. Anyway. Okay. So, yeah, and I can peel off, like, for example, let's say that I have a 64-bit width, but I fan by 8. What would that do? It would split it into 8-bit wires. Okay, which maybe I would need for some reason. I don't know. In particular, where we could use this sort of thing would be like, so let's think back to the Brookshire instruction set, right? Each instruction took 16 bits, but what were the first 4 bits? Those were the opcode. That told us what to do. And the second, third, and fourth 4 bits told us, well, register addresses or numbers or whatever, right? So we could take that 16 bits and split it into its 4 chunks of 4 bits and then have each of those 4-bit things going to whatever they need to be processed by, right? So an instruction decoder or something along those lines. Okay, so do you guys get the idea? I would just have to sit here and drag a whole bunch of wires. Okay, and then similarly on the output side, I would bundle it back up. The splitter both works as a splitter and as a combiner, right? So you can take 8 things and pipe them back into one. Okay, now physically, it's still 8 wires, but they're just bundled together, and that means that it's easier to keep track of on the computer. Okay, does that make sense? Yeah? No? Okay. Um, I mean, you could do that, right? In this case, like, if I only have one write enable bit, then I would be designing this thing where you would write all 8 bits simultaneously, right? If for some reason you didn't want to do that, then you would need a more complicated write enabling system. Like you would need to be able, like if you needed to be able to address individual bits, then our write enable would need to also be an 8-bit type thing. Okay. Um, and yeah. Okay. So this is basically how we would make both a register and RAM. Okay. The only difference, of course, is that RAM is going to be just crap tons more of this and is physically separate from the processor, right? So RAM is not on board the processor, registers are. Okay, now that's a little bit misleading nowadays because what do you have that's sort of in between RAM and registers? Cache, right? And in fact, on modern processors, there's multiple layers of cache, right? L1, L2, L3. And so that complicates it. But let's just pretend that cache doesn't exist for right this instant. Is that okay? Okay. Huh. Cache that also doesn't exist if you just ordered your RTX. In fact, out of curiosity, let's see if they're already sold out on Newegg, because I'm almost certainly they are, right? Yeah, that's true. And in fact, I noticed that, so because my birthday is in the not too distant future, Best Buy has like a get 10% off a selected item, and that applies to the 3070 and 3080s. I could buy one and sell it, and so let's see if they're sold out yet. Um, oh, they only have, I was hoping they'd have the Founders Edition ones, but okay. Let's see if we've got an Asus 3070. Hey, they still have it. Wow. Yeah. So, well, yeah, because it's overclocked and it has fancy RGB garbage and right. I mean, if I were going to buy it, I'd probably buy this one, but hey, that's shocking that they're still in stock. Let's check Best Buy. It's like that South Park thing, and it's gone. Right. Um, because Best Buy has the Founders Edition, meaning the ones that NVIDIA themselves produces. Uh, the manufacturers like Asus and whatnot. See details. Well, what are the details, pray tell? Well, but it should have launched at 6 this morning, Pacific time. So, whatever. Guess we don't get our graphics card. Womp womp. So, all right, anyway, back to what we're actually all here to do. Okay, so that's just a sort of quick taste of kind of some of the circuit schematic stuff we're going to do, because what are the different components we would need if we wanted to build sort of a processor? Well, we would need some registers. Okay, great. Um, and depending on what architecture we're designing, we could have however many of them we want. Classic Intel had basically four, plus like a status register and some specialized ones. Brookshire has 16 general ones. ARM has 32 general integer ones, although we've seen that some of them have special uses. Um, and what else would we need? Well, we need some sort of thing, and this is the hard part of it, a control unit. Okay, because what the control unit is going to have to do is all of these things that have like write enables and read enables and whatnot. If I want to read data from memory and write it to a register, I need to read enable on the memory, write enable on the register, and connect the appropriate data buses so that the bits get from one place to another, right? And keeping all of that synchronized is not, that's the hard part. Okay. Um, what else would we need though? Okay, so registers, we said that. Um, what else? A control unit, that's the big one. Well, we need an ALU, an arithmetic and logic unit, right? Okay, how do we build one of those? Well, how do we build a circuit that does addition or subtraction, or let's ignore multiplication and division for now because those are complicated. Okay, or rotating of bits. Okay, so let's think back to the Brookshire architecture, just because it's very simple. What instructions did we have? There were 12 of them. You had instructions that move data to and fro, okay, from memory to register, register to memory, register to register, and number to register. Okay, so there were four of those. You had addition of floats and integers as two separate things. Let's ignore the float part. Then you had and, or, not, and rotate. Yeah? Okay, and then you had the tough one, which was the jump. Okay, so could we theoretically build a Brookshire processor or simulate one in here? Yes. Okay, so that's the idea for what we're going to do for the rest of the semester, other than talking about the Gpio pins once I get everything working. Yeah, so this is sort of the transition point. We've been very software focused. Let's get a little bit more hardware focused. Okay. All right, the last thing I wanted to do, and this will be pretty quick, is I wanted to show you guys how to well, do two things. One is, so far, when you've written a program, how many assembly files have you generated? For each program, precisely one. Do you have to do that? No, of course not. And furthermore, you can mix C and assembly. Okay, so the reason that this may be useful to us today or next week is because what it means is that I could mix C and assembly for doing the GPIO stuff. Use the C library to basically give me access to everything, and then do what I want to do in assembly. Okay, okay. So let's just write a silly example of this. And I'll just call this mixed because we're going to mix C and assembly. All right, so let me write a C program that is going to do the following. It's going to I'm going to write a function in assembly that triples a number, okay, or doubles a number, whatever. And then I'm going to print it. Okay, like so. And let me save this real quick. So this is main.c. Okay, now what else do I need up here? Need the header for standard input output because I'm going to use printf. But then my func I have never defined yet. Okay, so what I'm going to do is I'm going to say extern long int my func long int. Okay, extern tells the compiler that that function is not defined here but in some other place. Okay, now we need to write the code for extern. Okay, but my function or my main routine here, oh, and I need to return 0, of course. Oh, thank you. Yeah, I've got to do that too. Okay, so I've got to do those two things. But how do I pass a number to this function, right? So I'm defining a function that accepts a long int as input and returns a long int as output. Okay, so when I write the assembly for this, where is the input number, in this case 3, going to be waiting for me? Register 0, because that's the calling convention, right? Where do you pass parameters? You start with register 0 of either float or integer, depending on which kind of, what data you're passing. Okay, so if I go to write myfunc.asm, all right, let me save this real quick. Okay, what's going to go here? Well, I need to have my data section, which there isn't any, my text section. All right, so what's the function got to do? Well, first thing, store and load. In this particular example, this isn't necessary because my subroutine isn't going to call other subroutines, but I'll just do it to cover my butt. Okay, so I want to, let's say, double the number. Where is the input number sitting? X0. Okay, so if I want to double it, then I can just do this, right? And do I need to do anything else other than return? Oh, thank you. Okay, so other than that, are we done? Yeah, okay. Because where should the answer be placed? Where is the C part of the program going to expect the output? In X0, okay? Because again, that's the calling convention for passing to parameters. Okay, so now what do we do? Well, need a new terminal window. Okay, so so now I've got two things that I need to deal with. I've got a C routine and an assembly file. All right, step one, assemble the assembly file. Okay, step two, let me just call it main. But now I need to do main.c and myfunc.o. Okay, so everything that follows so -o main would say the output is going to be the program executable called main. Okay, what input file or files do I need? Well, I have myfunc.o that came from assembly, and I have main.c that came from C. I could have 15 other things there, okay, if I needed to. All right, and then let's run that. Okay, and Gucci, now we're ready to run it, and it did that. Okay, so the C program, or the C part of it, passed a parameter to the other part of it, and yeah, okay, so we could do this. So what this means then, right, is, well, we could have done this with regular assembly too, right? We just wouldn't have had this C file, right? So let's say, for example, the fun with floats assignment, right? You're really computing the inverse square root in two ways. You're computing it with the magic trick, and you're computing it with the built-in stuff. Well, we could make each of those a separate assembly file and call them from a main assembly file or a main C file for that matter. Okay, does that kind of make sense? All right, and if you wanted to, like, let's say I wrote a function in C and I wanted to branch to it, what would I do? In assembly, I'd branch and link to that routine name. Okay, and I just have to make sure that if there were any input or output parameters, that I put those in the correct registers to do it. Okay, so hopefully by next time I'll have the GPIO stuff working because it'll be a lot of fun. And then we'll continue with our circuit level discussion. And for basically the rest of the semester, I think, at the rate things are going. So we are not too far off from the end. So anyway, and of course, there's no